aligns with their intuition that things should agree with constant acceleration, but that isn't the case in practice. Anyway, it's an explicit integrator, which is nice, it's fast, and it's accurate to first order. If we choose beta equals 1/2 and gamma equals 1, by the way, to get these formulas here, all I'm doing is plugging in those constants and simplifying a little bit. Then you get something that we call the constant implicit acceleration, where the only difference between this and the last guy is now we're using acceleration at tk plus 1 instead of tk. Right? So this one is stable and also first order accurate. And in fact, kind of an interesting property that holds here, you can see that we're using backward Euler to update v. And in fact, if you plug this expression into the expression for y, you can see that secretly we're using midpoint to update your position. Kind of a funny fact of the day. If you choose beta equals 1/4 and gamma equals 1/2, it's kind of cool. So this is generalizing the whole set of integrators we had before. Then you get the trapezoid method, right, which you can see is nicely democratic here, and is second order accurate, and also I think stable. And the trapezoid method still, even this trapezoid method, which is second order, still suffers from some of that weird oscillation behavior we talked about before. I'm going through these quickly because they're really not humongously important. And finally, if we choose beta equals 0 and gamma equals 1/2, we get this really interesting central differencing scheme. It turns out after a little bit of algebra, what's really going on is that you're putting the accelerations sort of at the midpoints of your position, of your velocities, and your velocities at the midpoints of your positions, and so on. And so you get this nice sort of democratic scheme for integration. So anyway, in practice, you'll see all kinds of different schemes. Oftentimes, again, what I'll espouse in this class, which is obviously a very kind of fast-paced survey intro class, is that you just try a few of them and see what works for the problem you're trying to solve. Yeah? So in general, for numeric schemes, again, it's this large class of different OBE integrators, right? Each choice of gamma and beta gives you a different integrator. You can show, although the proof is highly non-trivial, I tried, that you get second order accuracy exactly when gamma is equal to 1/2. If you choose any number for gamma other than that, it's first order accuracy. Well, by construction, it's first order accurate. Right? We actually just, we made it that way. Yeah? And it's, there's also a sort of a similar condition for when these things are unconditionally stable. Otherwise, you're going to have to, for a particular choice of beta and gamma, there's some formula that tells you the radius in which this is stable, and it's a nonlinear weird formula. Such as life. Okay. For my final trick today, and then we will be done with these time-stepping schemes once and for all, at least until we consider the heat equation on Monday, we're going to talk about the staggered grid method. Now, remember, this goes back to when I was talking about how we computed derivatives, right? When we computed the derivative of a function, right? So if I had yk and yk plus 1, right? And we think of this as time here, right? Then if I did the divided difference, right, I subtracted these two guys divided by dt, then, you know, if we said we were doing forward differencing, then the derivative lives here. If we're doing backward differencing, it lives here. If we're doing midpoint, it lives there. But somehow, democratically speaking, if you don't know where to put your divided difference derivative, it kind of makes sense to put v here, right? Because, like, you know, anything else you do is inducing error. In fact, you saw it, right? It's a first order approximation of the derivative at these two places, a second order in the middle. Yeah? So in fact, what these staggered methods do is they say, okay, well, so be it. So we're just going to stick the velocities at the midpoints of the positions and leave them there and not make any approximation. Right? And then, well, okay, what if, let's extend this a little bit to yk plus 2, right? And now we're going to say we have vk plus 3/2. Yeah? Then what's going to happen to the accelerations? The accelerations are going to live back on the integer points because they're sort of averages the velocities. Right? This is called a staggered grid method. It's also used a lot in fluid simulation. For example, if you have a fluid that's on like a three-dimensional sort of polyhedron of vertices, then you'll think of the velocities of your fluid as living in the edges, and the positions, you know, the densities living in different places, and so on. And basically what the staggered grid method says is, who cares where your velocities are? Just leave them wherever they land, and don't try and move them somewhere else. Totally reasonable. Yeah? So in fact, you can see that in this formula here. That how are we going to find yk plus 1? Well, it's quite easy. Well, you start at yk and you add some multiple of vk plus a half, and the nice thing is that that formula has higher accuracy than if you'd moved v to either of the 2 endpoints. Right? Similarly, to time step v, what are you going to do? Well, you'll take the v at the previous half time step and the acceleration halfway between the 2 v's. Right? Now, in the Staggered grid method, we are going to have to cheat a little bit, because you also have to evaluate this acceleration, right? And unfortunately, remember, the acceleration is a function of time, position, and velocity. And it's that third one where you get a little bit of a headache. Right? Because remember that we want the acceleration here, but we only have velocities of these 2 Staggered grid points. Right? So what do? Well, we cheat. We just average the 2 velocities, and since this is a higher order term, that's okay. Right? So this is another instance of one of these methods where our accelerations are not particularly accurate, but that's okay, as long as our velocities are accurate. Or our positions, rather. Yeah? And in fact, in one special case, this turns into a nice method that's in fact explicit. We call it leapfrog. And that's when your accelerations only depend on your position. So let's say that I'm solving a system of springs, which actually is a very common use case. Right? So I have a bunch of different particles, they're all tied together by springs, and they're moving around over time. Yeah? Then in particular, the force is a function only of the configuration of my particles, right? Because that determines how stretched out the springs are. Right? Well, in that case, well, this weird averaged out term actually just goes away. Right? You see that? Now it's just a function of t, not even t, just of x, right? The leapfrog method is really nice, because if we know these 2 guys, right, well then I can jump y forward, and now if I know v, and I know y at the midpoint, I can get a exactly at the midpoint, because it has no dependence on velocity here, and so I can jump v to the next guy, and so on. That's called a leapfrog method. And it is, it's got nice accuracy, it seems to be very popular among physicists. Now, if you do have v dependence, then life is not nearly as good, but thankfully, usually the v dependence, at least in physical systems, has this nice property, where let's say that I'm like running, and I feel wind resistance, then it's pushing me backward. And now if I turn around and I run in the other direction, then wind resistance is going to push me the same amount just in the minus direction. Right? So usually what happens is when I do implicit solves in a staggered grid method like this, at the very least the matrix that I'll be using to solve will be symmetric and positive definite, and as we hopefully know from this class, that is a very happy case to be in. Yeah. So anyway, I think that concludes our lecture for today. So that's the end of our consideration of ODE. On Monday, or not this coming Monday, no class next week, but the Monday after that, we'll start talking about PDE, right? Things like heat and waves, and what's the third PDE everybody cares about? Heat, waves, and rubber sheets. And we'll learn how, if you have to combine derivatives both in space and time, how you can do this in a careful way to solve these different physical phenomena. And then that's the end of this class. So anyway, get your work together, you're almost done, congratulations in advance, and yeah, I'll see you after Thanksgiving.